Hello viewers, in this series of alkanes and cycloalkanes, we have discussed in previous episode about the introduction of cycloalkanes, nomenclature of cycloalkanes and the methods of formation of cycloalkanes. In today's episode, we will discuss about the physical properties of cycloalkanes, chemical properties of cycloalkanes, ring strain in cycloalkanes along with bare strain theory, limitation of bare strain theory and the theories of strainless rings. So, first we will start physical properties. Cyclopropane and cyclobutane are gases, next three members are liquid and higher members are solid. These are insoluble in water, but soluble in alcohol or acetone. Their density increases with increase in molecular weight. Lower members are lighter than water and floats over it. It is therefore, cyclohexane floats over water. The boiling points increase with increase in molecular weight. The boiling point are also higher than their corresponding alkenes and alkanes. Most cycloalkanes resembles the acyclic open chain alkanes in their physical properties. There are nonpolar, relatively inert compounds with boiling points and melting points that depend on their molecular weights. So, the cycloalkanes are held in a more compact cyclic shape. So, their physical properties are similar to those of the compact branched alkanes. Due to the compact structure, melting points and boiling points of cycloalkanes are more than the corresponding open chain alkanes. It has been given in a table as follows. This is the alkane, that is propane, and this is the cyclopropane, having a difference in their boiling points due to the presence of higher molecular weight difference, and same as in butane and cyclobutane. Here is a difference in between boiling points and melting points. In pentane, cyclopentane, we are further seeing that pentane is having 36 degree Celsius boiling point, rather cyclopentane is having 49 degree Celsius boiling point. It is clearly indicating that due to the increase in molecular weight, the boiling point is also increases, same as in melting points. Hexane, cyclohexane also having the great variation in their molecular weights. So, the boiling point you are seeing that is also increasing, as well as melting point is also increasing. In heptane and cycloheptane, further we are focused on their molecular weights. So, heptane is having boiling point that is 98 degree Celsius, rather cycloheptane is having 118, that is 118 degree Celsius boiling point. The same reason is here. Now, we will discuss the chemical properties of cycloalkanes. Cyclopropane and cyclobutane are comparatively less stable due to more strain in ring and thus tend to break up and open the ring to act like a double bond species to give addition reactions. The cycloalkanes from cyclopentane and onwards show remarkable similarities with alkanes due to their stability. The stability of higher cycloalkanes is due to less strained ring as well as each carbon atom being sp3 hybridized like alkanes. It is therefore, higher cycloalkanes are not attacked by acids, alkalis and common oxidizing agents under normal conditions. Since cyclopropane and cyclobutane bear high angle strain, they are highly reactive and they behave like alkanes. In some cases, other cycloalkanes behave like alkanes. Some of the important chemical properties are as follows: substitution reactions, addition reactions, oxidation reactions. So, first we will study substitution reactions. In these reactions, when cycloalkanes are treated with chlorine or bromine in presence of a catalyst or UV light, halogenoalkanes are obtained. In halogenation reactions, cycloalkanes undergo chiefly free radical substitution in presence of sunlight or UV light like alkanes. Here we can see the chemical reactions of halogenation by using chlorine and bromine at various temperatures. Cyclopentane, that is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Cyclopentane when react with chlorine at 200 degree Celsius temperature, we get chlorocyclopentane. This is the substituted product along with HCl, and when cyclobutane react with bromine, we get bromocyclobutane. This is the cyclobutane because it is having cyclic structure along with 4 carbon atoms, and this is the bromine which has been substituted hydrogen from this corner, and we get HBr along with this bromocyclobutane. Cyclopropane when react with chlorine in presence of light, we obtained chlorocyclopropane along with HCl. Now, we will discuss addition reactions. In these addition reactions, first we will describe about the addition of chlorine. Cyclopropane reacts with chlorine in the dark to form open ringed addition products. In this reaction, we are seeing that cyclopropane when react with chlorine in presence of FeCl3, we get open ring structure here, that is 1,3-dichloropropane. These are the chlorine atoms on carbon number 1 and carbon number 3. So, the name of this compound is 1,3-dichloropropane, and when cyclopropane react with H2SO4, then further we are seeing that ring is opening, and this cyclopropane is converting into propanol. In another addition reaction, we react cyclopropane with concentrated HBr and get 1 bromopropane. As this reaction is showing that this cyclopropane when react with HBr, we are getting open ring structure, that is 1 bromopropane. When 1,1-dimethyl cyclopropane react with HBr2, we get open ring structure, or you may say the open ring compound 1,1-dimethyl propane. These methyl groups attach with this carbon atom. So, the name is 1-bromo 1,1-dimethyl propane. Cyclopropane reacts with hydrogen in presence of nickel catalyst to yield normal propane. So, we may say that these reactions are also ring opening reactions. Cyclobutane react with hydrogen in presence of nickel catalyst at high temperature to yield normal butane. In these reactions, we are seeing that cyclopropane when react with hydrogen at 80 degree Celsius temperature, we get normal propane, that is straight chain compound. When cyclobutane react with hydrogen at 200 degree Celsius, we get straight chain compound, because this compound is having 4 carbon atoms, carbon 1, carbon 2, carbon 3, carbon 4. So, according to IUPAC nomenclature, 4 carbon are to be said but. But in cyclopentane when react with hydrogen molecule, then no reaction takes place. Now, we will discuss oxidation reactions of cycloalkanes. In it, cycloalkanes are oxidized by alkaline potassium permanganate to dicarboxylic acids. As in this reaction, this cyclic structure, or we may say that cyclohexane, after oxidation in presence of alkaline KMnO4 converted into adipic acid. It is the open ring compound. Now, we will discuss the types of ring strains in cycloalkanes. Basically, these are of 3 types, that is torsional strain, steric strain and angle strain. So, first we will describe torsional strain. It is the strain which originate by the eclipsing of bonds on neighboring atoms. In this structure, we are seeing the condition that this hydrogen atom is eclipsing by this blue hydrogen atom. So, it is the type of torsion strain. Next is steric strain, the strain due to the repulsive interactions when 2 atoms or groups approach each other too closely. It is shown in this structure that these both groups are on similar side. so having higher energy, but less stability. And in this structure we are seeing that one group is at the plane and another is far away from the plane. So, we may say that it seems to be like a chair form. So, it is having lower energy, but it is highly stable. Now, we will discuss angle strain or ring strain. Ring strain occurs because the carbons in cycloalkanes are sp3 hybridized, which means that they do not have the expected ideal bond angle of 109.5 degree. This causes an increase in the potential energy and desire for the carbons to be at an ideal 109.5 degree. An example of ring strain can be seen in the diagram of cyclopropane, where the bond angle is 60 degree between the carbons. This diagram shows ring strain which arises due to the expansion or compression of bond angles. Now, we know that sp3 carbons like to bond at 109.5 degree, but it is having 60 degree bond angle in cyclopropane. So, we may say that there is a angle strain. In this table, we can easily find out the strain, or you may say the angle strain. Cyclopropane having bare bond angle of 60 degrees, rather the fixed angle is 109. So, 109 minus 60 is equal to 49, that is the angle strain in cyclopropane which has to be observed. Cyclobutane is having 19 degree angle strain, cyclopentane is having 1 degree angle strain, and cyclohexane is having minus 11 degree angle strain. In 1885, the German chemist Adolf von Baer proposed that the instability of 3 and 4 membered rings was due to angle strain. We know that ideally an sp3 hybridized carbon has bond angles of 109.5 degree. Baer suggested that the stability of a cycloalkane could be predicted by determining how close the bond angle is of a planar cycloalkane is to the ideal tetrahedral bond angle of 109.5 degree. It indicates that due to the strain, the geometry of compound can be changed, or you may say that due to the strain the angle can be changed, that is we may say that the angle can be changed in cyclopropane is 60 degree instead of 109.5 degree. The less effective orbital overlap is what causes angle strain, which in turn causes the carbon carbon bond to be weaker than a normal carbon carbon bond. Because the carbon carbon bonding orbitals in cyclopropane can't point directly at each other, they have shapes that resemble bananas. In this structure we can see the shape just like bananas, and consequently are often called banana bonds. In addition to possessing angle strain, 3 membered rings have torsional strain because all the adjacent carbon hydrogen bonds are eclipsed, which we have already discussed in the type of angles. Planar cyclobutane would then be expected to have less angle strain than cyclopropane, because the bond angle in cyclobutane are only 19.5 degree. So, we may say that as the number of carbon atoms increases in the compound, the strain decreases as usual. So, cyclobutane are only 19.5 degree away from the ideal bond angle. Now, we will discuss that what is the impact of angle strain on overlapping of orbitals. In this figure, we are seeing that it is having good overlapping and strong bond, or we may say that due to the absence of angle strain, the overlap of sp3 orbitals in a normal sigma bond is having a good overlapping, or we may say that having strong bond. And in figure B, we are seeing that due to the angle strain, it is having poor overlapping or weak bonds. Due to that, the overlap of sp3 orbitals in cyclopropane are weak in nature. Now, we will discuss the heat of combustion. It is the energy released as heat when a compound undergoes complete combustion with oxygen under standard conditions. This table shows the comparative study about the carbon atoms, heat of combustion and total strain. We are seeing that as the carbon number are increasing, the heat of combustion decreasing along with the decrement of total strain. But after carbon number 6, as we are going to carbon number 7, the sudden increment is going on in the heat of combustion and total strain is also increasing in comparison to cyclohexane. So, we may say that cyclohexane having much less strain in comparison to others. So, cyclopropane and cyclobutane evolve more energy per methylene group than an open chain compound, meaning they contain more energy per methylene and hence less stable, which is in agreement with the bare strain theory. Now, we will discuss the limitation of bare strain theory. Heats of combustion data indicates that Bayer's theory was not fully correct, as we have seen the little bit deviation in the strain and heat of combustion and in carbon numbers. So, cyclopropane and cyclobutane are quite strained, but cyclopentane is more strained than first predicted, while cyclohexane is less strained, as we have discussed. For larger rings, there is no regular increase in strain and rings of more than 14 carbons are strain free. Bayer assumed that all cycloalkanes are flat, when in fact most adopt a puckered 3D conformation. Furthermore, he did not consider the contribution of torsional strain to the overall strain energy of a molecule, which has been seen in previous table. Now, here we have certain examples which shows the Bayer strain theory. As for example, cyclopropane, it is having the most ring strain alkane ring 60 degree, which is showing in this figure, instead of 109.5 degree. It is due to the strain. The two hydrogens eclipsed each other. These two hydrogens are eclipsing each other. Bonds are weaker and more reactive than any other cycloalkanes. Another example is cyclobutane, 4 carbon atoms in cyclic structure. The most torsional strain alkane ring due to the increased number of hydrogens. Because of the increased torsional strain, the total energy of cyclopropane and cyclobutane are the same. Bayer concluded that cyclopropane would be the most strained, followed by cyclobutane. Cyclopentane would be strain free, while cyclohexane would show a substantial amount of strain energy. Rings larger than cyclohexane would be impossibly strained and not capable of existing. In next topic, we will discuss the theories of strainless rings. In order to account for the stability of higher cycloalkanes, Sachet and Mohr proposed a theory of strainless rings. According to this theory, the ring with 6 or more carbon atoms becomes free from strain, as all the ring carbon atoms are not forced into one plane. Carbon atoms occupy different planes where the normal tetrahedral angles are retained. The rings formed are called strainless rings. Cyclohexane having two conformations as chair form and boat form. Both these forms are without any angle strain, hence they are strainless rings. So, chair form of cyclohexane is more stable than the boat form due to the following reasons. In the chair conformation, the adjacent carbon hydrogen bonds on all the neighboring carbon atoms are staggered. In the boat form, the adjacent carbon hydrogen bonds on carbon number 2 and carbon number 3 and carbon number 5 and carbon number 6 are eclipsed. Hence, energy of boat form becomes more than the chair form. So, out of the 12 hydrogens, 6 of them point up or down perpendicular to the plane of the molecule. These are called axial hydrogens, which has been shown in next structure. The other 6 hydrogens are found either above or below the plane of the molecule. They are equatorial hydrogens. In the boat form, the two axial hydrogens on C2 and C4 are closer than in chair form. Hence, the energy of boat form is more than the chair form. Cyclohexane is strain free, which means that it is stable. In previous discussion, we have come to know that there are two chair forms and one boat form. The boat form is a transition between the one chair form and the other. It is to be described in this figure. If you look closely, then you will see that if the red carbons bend up, you will have the boat. If the blue carbon bend down, then you will have the second chair form. So, we may say that this boat form is a transition form in between these two chair forms. Viewers, in this episode, we have discussed about the physical and chemical properties of cycloalkanes, types of ring strain in cycloalkanes along with bare strain theory and its limitation, and theory of strainless rings. So, viewers, I hope that you have enjoyed this unit along with the introduction of alkanes, IUPAC nomenclature of branched and unbranched alkanes, isomerism in alkanes and methods of formation of alkanes along with the physical and chemical properties of alkanes and the mechanism of free radical halogenation along with orientation, conformation, reactivity and selectivity, and introduction of cycloalkanes, nomenclature of the same along with the method of formation of cycloalkanes. This unit will definitely beneficial for your further studies of BSc first year organic chemistry, and I hope that you have enjoyed a lot of this unit.